So this is where we left off. We're looking at this group problem. I guess I did copy down here. I was just seeing if I had gone over any of it, but it looks like I haven't. So we're doing this first group problem associated with power to see if we've got the basic concept. So we're looking at doing parts A, B, and C of this problem. So how far did we get before we had to stop? So A and B you got to? Okay. So why don't we go over at least parts A and B, and then you guys, if you're on C or whatever, you can finish that up later. So we're looking at, for this problem, so in part A here, we've got the null hypothesis that mean is greater than or equal to 12, and the alternative hypothesis. Okay, sigma is 2, n is 100. So let's see, we have this one-sided test. I guess I'll draw it right here. B is equal to 12. And over here at x bar equals 11.7, we're defining our rejection region. So I'll zoom in. That's a little hard to see. So this, excuse me. So our x bar star, our hurdle value is 11.7 for the mean. And then anything smaller than that, we are going to reject the null hypothesis. Do you have that picture drawn? Okay, so for part A is just asking, for that situation, for that hurdle value of 11.7, what is alpha? So that corresponds to a t-value of over 2 square root of 100 minus 1.5, and that's z because we've got lots of samples. We've got 100 samples. And then that corresponded to an alpha of 0.0668. Seems to me I wrote that last time. Did we go over that part last time? Okay, good. So alpha was 0.0668. Good. So then part B. Any questions on part A? That's the basics of it. Part B now is where is the newer stuff. So now we're asking a question about our hypothesis testing procedure. Yeah, Chris.
Question about part A. So they just decided x bar is lower than the number to reject the hypothesis without even testing it?
Yeah, so they don't give you any information why they chose that number. So it's just, I think, a way of giving you different information to do a problem. Normally you have alpha, right? So, and typically in the real world, you're going to choose an alpha, and that will give you a z star and an x bar star. So now for part B, it says find the power of the test to detect the situation in which the mean really isn't 12, but it's 11 and a half. Right? Okay, so for part B, we say this is the hypothesis testing procedure, and we're asking what if the distribution is not centered there at 12, it's centered here at 11.5. And keep in mind, I think it's always good to draw these things like this, one below the other, and connect them through this hurdle value. That's how the two distributions are connected, or if you will, the two parts of the problem are linked through this hurdle value. And so it's saying, what's the power of this hypothesis, the test, to detect this shift in the mean, or if the mean really is not at 12, it's at 11.5. So we're going to look at the area underneath this curve, right? So when we get our x bar, is it going to come from this distribution down here or this? So when you go out in the lab, if this is really true, if the mean drying time really is 11.5, when we go collect 100 data points and average them, that's going to come from this distribution down here, this red one, right? If that one is true, your data is going to come from that distribution. So it's going to drop out somewhere here. So we've got two areas. One corresponds to power, one corresponds to beta error. So which one's power, which one's beta error? I've got blue and green. What's blue? Is that power or is that beta error? Power, right? That's power because that's how often we're going to make the right decision. The right decision in this case would be to reject this null hypothesis. And we're going to do it any time we get an x bar star that's in the rejection region. And beta is, green is the beta error. So if we want the area underneath this red curve here, we know this is 11.7. We need to find the t-value that's associated, or excuse me, it's z, because there's so many data points, associated with this distribution. So we've got 11.7 minus 11.5 over that, and that gives us 1.0. So the probability then that z is less than 1.0 is 0.8413. Does that make sense? So the power is 84%. All right, and that, I know we went over that before as well, but it's good review. So let's see if okay, so now for part C, what are we asking? It's saying for what values of x bar, I guess, should h naught be rejected so that the power of the test will be 90%. So for part C, it's asking now, we're going to redo this calculation, but let's shift this line so that this power is 90%. Does that make sense? So we're saying we're going to shift this line over. Right now it was 84%. Let's move this line over this way, right? So people that are getting this on the video. So we're going to shift that line over. So that equals 90%. And then it's asking, what will the level be? So it's saying, well, what happens to that alpha when that line shifts over? So has anybody finished that part? All right, do that now then. Yeah. Oh, okay. So go ahead and quickly do that. Question?
So my question was, well, we won't ever know the true mean if we're actually doing statistics, right?
Right.
So why is this kind of problem applicable to statistics?
Oh, it's very, because you will know, probably, that if you're doing some hypothesis test, you're saying, okay, we've got this test set up, and for some reason, if the mean drying time is 11.5, we're going to be in trouble. So what's the likelihood, if the mean drying time is 11.5, that our test picks up on that? And our test, as it's designed, 84% of the time, it will find that. Does that make sense?
Yeah, so, well, in this case, you wouldn't be in trouble. You want the drying time to be small, right?
Depends.
Well, in this specific case, it says
Yeah. So in this case, it looks like we are trying to reduce it. Yes. So it could be something where that would be really, really good. We could claim that. And so we want to determine that would represent a significant advantage over competitors, and we'd like to find that out if it's true.
it's not a double hypothesis,
Well, think of it as we have some hypothesis test, and then we're asking an extra question about that, about the test itself, about the procedure. Is it sensitive? I think it's a way to say it is, how sensitive is this test? Will it pick up what we want to pick up? Yeah. Oh, okay. No. So power is, so we have power and beta here and levels up here.
Oh, I see.
Yeah, so level is associated with the hypothesis test, and then power tells you some information about, well, in. So you use 90% to get this, right? Yep. Then you bring this up here. Yep. Yes, that's right. Okay. People still working on C. Did you guys get C done? Okay. You guys get C done? 11.24 for, so it's asking for alpha, the level? Oh, for this number right here? The X bar star? Let's see. All right. Well, let's go over it and see then. Okay. For part C, we're going to get rid of all this. This is part B. And we'll get rid of this as well. For part C, we're trying to figure out where is the cutoff value so that we get a power of 90%. So we use this 0.9. You go to your standard normal distribution table, and that will give you some z value. Anybody get a z value there? One of our friends that we see a lot, 1.285. Does everyone get that? Okay, so that will be the z value associated with our cutoff value, so our z star. So that's minus so the cutoff value in units of x bar, if you will, you got 11.757. Anybody get that? Good. Okay, so again, it's very important to know that it's the same line here as it is up here. The cutoff value is the same rejection region. So now we drop up to our hypothesis test, and we say, given that, what is alpha? So from that, we need a z star. So we have 7 minus 12. I got, so minus 1.215. Anybody get that? Who got that? Some people got that. And that corresponds to an area. You look it up in the table. I got an alpha of 0.112, so 11.2%. So let's generalize. When we move from part B to part C, what did we do to power? We increase it, decrease it, keep the same. When we increased power, what happened to alpha? Increased, right? So we tried to make the power better, and it made our alpha error worse, right? So think about that trade-off between type 1 and type 2 error, alpha and beta error. If you're shifting this line around, if you make one smaller, you make the other one bigger, the errors. So there's a trade-off between alpha error and beta error. Okay. All right. Any questions about that example? So just remember these power calculations. You first set up what is the hypothesis test I'm doing. Make sure to define the rejection region because that's going to link what the next question is. And then I'm going to ask some what if question. What if the mean really is this? What's the power of my test to detect that? Or how sensitive is this test to determine this situation? Okay, so I think people get in trouble if you don't clearly define your rejection region, and then you don't know how the two distributions are linked up. Okay, so now we're going to keep playing with this power calculation, and what we've done before is we did what you could think of a sequential solution where we could work all nice and tidy with the first distribution and then drop down to the second distribution and work on it. So now we'll look at the one situation in which you could think of it almost as a simultaneous solution where we'll have to look at, get equations for both distributions and then set them equal to each other. Okay. So here in our notes, so I better go here. So I'm going back up a page in your notes to here. So let's read through this example real quickly, and let's just think about what we're doing here. So our hypothesis test looks like this. There's the rejection region, right? Haven't got all the information down, but we have our null and alternative hypotheses are given to us. We've got the rejection regions based on alpha is 5%. The null hypothesis shows mu at 80. And now this is saying, well, what if, again, the what if question with power is if the mean really is at 81, and then again I better extend that line down so I can see how the two distributions are linked. I've got a mean at 81. I want the power to be 90%. Did I put it in the right area? Is that power, not beta? Okay, it is power. And so we want to find n, right? So let's think about that. That's all the information of the power. Remember what n does to both these distributions? It tightens them up, right? So you could think about, you could increase n, both of them tighten up. Alpha goes down, beta goes down, power goes up. Or as n decreases, the other thing happens. And so we need to figure out that n. So we can't get, it'd be nice if on this top distribution we got a z star. And on the bottom distribution, we would have, we know those, and an x bar star. We know those x bar stars are the same, right? So whatever that value is, it's the same there. Does everyone see that? That's pretty important. So just maybe take a minute, convince yourself that those two numbers are the same. That's what that vertical line means. X bar star is the same in both of those. So in this case situation, we can't just use the top distribution to find x bar star, right? And we can't use the bottom distribution just to find x bar star. So we need to use both distributions at the same time. So why don't you take a minute, work through that, see if you can get that. Can you get a z star for both distributions? Yes, I would start there. Ah, yes. We made an assumption to get this started. I think you guys are talking about that back there. And that's a critical thing. We'll talk about that when we get through that. So let's find the z star, but then we'll talk about, we had to make a pretty bold assumption that we need to really check at the end. Because one's on one side of the mean, one's on the other. Right? See, and this one on the right, on the left. All right, so now let's take a look at this. So from this top distribution, we can get an expression for x bar star, right? X bar star minus the mean of 80 divided by 5 over the square root of n, whatever it is. For the bottom one, that's going to be the same x bar star minus the mean of that distribution divided by 5 over the square root of n. So now we have two equations, two unknowns, right? Unknowns x bar star and n. So you can just, you could solve this one for x bar star, solve this for x bar star, and then set those two equal to each other, solve for n. But you know how to solve for two equations, two unknowns. N ends up being 214 when you do that. Does everyone see the two equations and how we got them? This is one equation. This is another equation. They both are x bar star and n. The same x bar star, the same n in both equations. So in setting out this problem, I told you to go look up a z star. What did I assume when I threw down a z star? What's that? Well, the one-sided was given to us by the hypothesis test. But instead of z, what else could you have looked up? Could have done t instead of z. So I assumed n was greater than 30 and looked up the z's. And then at the end of it, I better check that n is greater than 30. And it's right in this case. But, yeah.
I was just going to ask, if you use t, since the t value is based on the n, how do you even...
Yes. It's sort of a light show for us. So now the question is, what if n was 20? How would we have proceeded? Because there's an extra complexity with t, right? Especially when you're solving for n. Because to look up a t value, you have to know an n. You have to know n to get degrees of freedom, right? So then it's iterative. We all like iterative solutions. I think students are always really excited whenever we have to iterate. So if this n ended up being 20, what we could have done is say, okay, assume n is 20, then I'm going to look up t stars with 19 degrees of freedom, set it equal, calculate another n. It's not going to be 20, it's going to be something else. And then look up a new t value and keep doing that until you converge on a solution. That's terrible. It's not fun. Or you could set it up in Excel and use, how can you make Excel do iterations like that for you? What do you use in Excel? Anyone ever used it? There's two ways of doing it. What function? There is a t distribution function. That'll give you your t instead of looking up in the tables. But how do you get it to try different n's until it converges on a solution? Yes, you could program, you could get into the Visual Basic programming of Excel, but there's a built-in function that's sort of built in to Excel. The solver. Who's used the solver? Where'd you use the solver? Double E stuff? Some are at work. Anyone else use the solver? Anyone use GoalSeek? It's like the baby solver. No. Okay. We should talk about that. The solver, it's in the data analysis tool pack in Excel. You got to add it in, otherwise it's there, but it's sort of hidden. The solver function is a way you can do iterative stuff in Excel very nicely. And so what it is you set up your equations and you tell Excel, change this number until this thing happens, until this equals 0, or this is maximum or minimum. So, all right, well, we'll figure that out later. Okay, so this is when we're looking for how many data points do we need to take to get an alpha and beta that we want. That's a very, very practical thing we're getting at, but it's a little bit more complicated. And so that's why in the group problem we didn't do that part yet, but we'll do it now. So now for part D, this is a continuation of part C, and then which changes the setup a little bit. Then for part E, it's saying, given what you did in part D, now do this, get two equations and solve for n. So again, in part C, we found alpha was 11.2. Now it's saying go back and redo this so this alpha is 5%. So initially we got whatever 6.68%. We got 11.2. So now it's saying move this bar over here, find x bar star so that alpha is 5%. And then once you do that, then it's asking that sample size question. if you're not drawing all that, you're probably going to get into trouble. Again, Part D is a lot like Part A. Pretty straightforward question, beginning of Chapter 6 stuff. Did everyone get 11.671 for Part D? No? Some people did? Did you get a negative value for that? So if you're on that side, that z star is going to be negative. Oh, yeah, yeah. I think it should be 1.645. You know, that 5%. Yeah. But it was close. All right, everyone okay with 11.671 for Part D? Great. So let's set up Part E. Make sure to draw that picture, right? It's a power question. You're going to have two distributions. You're going to have some rejection region line going through both of them. And then please shade in the areas, label power, label alpha. You can label beta if you want. One thing about the book is they don't always ask the question as precisely as I would like them to. So for this, when it says a power of 0.9, that's for the situation when mu is really 11.5. So if that's not clear, I tried to, actually I added this for parts B through E. I changed the way the book wrote it to try to clarify that it's for that situation. So you can't really do a power test to see how sensitive your procedure is to detect a certain situation unless you know what that situation is. In this case, the mean really is at 11.5. So now, armed with that information, if you drew that much, then you have a real fighting chance at getting the right answer. If you just take the time to make sure to draw the picture right, then you can concentrate on how can I get information from this distribution and from this one. It's one of those where n is unknown, so we're going to have to get two equations and solve them simultaneously because we don't know x bar star and we don't know n. What's that? So I got 0.05% for alpha here, right? So 0.05. That's 0.005. So it should be 1.645. So your z is minus 1.645 here. So, okay. And keep in mind you don't know n yet. Oh, you're doing d. Okay, I'm sorry. And so, okay. Yeah, fine. Yes, yep. We're using, it's because the n is different. The x bar star will be different. Is anybody done? Anybody get it? What'd you get for an n? 137? I think that's what I got. That's what I got too. Anyone else get an n of 137? Okay, good. All right, so here's the situation. We recognize the hurdle value for the mean. That's what this x bar star means. So the hurdle value for the mean is the same in both those distributions. So so we don't know what that is, and we don't know what n is. But here we could get a z star of minus minus 1.645. And then write that equation. So there's one equation. Using this distribution here, the z star is power of 90, so we have that 1.285 equals there's the other equation. Solve those simultaneously to get n equals 137. I solve them both for x bar star and then set them equal to each other. Keep in mind, it's easy. If you don't draw the distributions and think things through, you're probably going to get these things wrong. The 12 up here and the 11.5 down here. It's easy to get mixed up there unless you draw the distributions clearly and think through, I'm working with the top distribution or I'm working with the bottom distribution. And remember, the concept of power is we are doing this hypothesis test and we're saying, given this procedure, how sensitive is that test to detect this situation? Okay. That's what before what I said, we're going to try to, remember we talked about statistical significance and statistical importance, and I said, well, if some effect we're trying to discover is this big, we want to set up our test so that it detects differences this big. And that's where, when I say this big, that would be this 11.5. If that's the size of an effect that we really want to make sure that we detect, we'll do a power calculation and we'll say we need at least 137 data points to find an effect that big 90% of the time. If our power is really, really low, then we're only going to find differences that are really, really huge, right? Or this is shifted way down here. So the concept of power is really important, and it's going to come up time and again in the rest of the class, and it should come up every time you do any sort of experiment, because you are going to take some finite number of replicates, and that is going to determine the power of your test. Yeah, yeah.
When we solve for x star after 11.867, why didn't we just use that?
Oh, great question. Had that question twice. So for part D, we solved for this value, but we couldn't use it down here because this value was based on that. Right? So we had the same z star of 1.645, but that is x bar star minus 12 over 2, and in the first case it was square root of 100. Here in the bottom one is 137. Great question. A lot of people had it. Okay. Other questions on power of the experiment? So keep that in mind. Anytime you see a publication that says this was tested and the researchers found no significant difference, the first question in your mind was, I wonder what the power of their experiment was. If it was low power, then it's not a surprise they didn't find any significant difference. They didn't do enough repeats, or they didn't control the noise well enough. But if it was a high power, if it was over 90%, then you say, okay, that is some information, right? That is telling me something, that maybe there really isn't much of a difference in those two things that they tested. Does that make sense? So again, that's really, really important type stuff. So that's why there are books. One of the books I considered for the class at one point was How to Lie with Statistics, but the title is a little edgy. But the idea is people do this. You can make it seem like this is happening when it's not. And one way that people lie using statistics is do a low power test. And then you don't find anything, and if you didn't want to find anything, then you've accomplished your goal. All righty. A couple more concepts. So we're going to hit a few concepts here and there that just to clean up the rest of chapter 6. And these are concepts we're going to carry forward to the rest of the class too. The next one is this multiple testing problem, and it harkens back to the multiplication principle that we learned back in chapter 2. So when you have different events, it also has implications for what you learned in maybe logic in nature, principles of nature, I guess it is now. It used to be logic in nature, maybe logic, maybe ethics. When you talked about slippery slope, so we talked about a slippery slope fallacy. What did that involve when you talked philosophy? You guys all love philosophy, right? Come on, it's great. There's a lot of great stuff there. You should have seen when I had a great electrical engineering analogy that I would teach my chemical engineers at UND, and they almost revolted. They hated it, and it was rate determining step. It was all nice. Anyway, this is like this, where you should embrace it. Okay, slippery slope argument. What does that mean? When you learned about it in philosophy, what did they say? Why was it bad? Yeah. Okay. Right. You do something, and that leads you to something else. So the one that always sticks out in the mind is if you drink a Coke, then that will lead to you drinking alcohol. Right? You should know that. And then you're going to get into other gateway drugs, and you're going to smoke marijuana, and then you're going to smoke crack, and so forth, and do all those things, right? So you better not drink the can of Coke. That's that gist of the slippery slope argument here, okay? So why is it a fallacy? Because this doesn't necessarily there may be some link where by drinking, people that drink a lot of Coke may end up drinking a lot of alcohol. I do like drinking wine, and I do like drinking Coke, so I'm right here. Okay, so just teetering on the brink there. And so why it becomes a fallacy, or I should say, is it always a fallacy to say that, well, this behavior leads to something else? No, it's not. So how do you distinguish between a slippery slope fallacy and something that's reasonable, that this bad behavior might lead to this other bad behavior, or this questionable behavior leads to bad behavior? So there's really two things that make this a bad argument. One is, as Chris mentioned, that this necessarily causes this, or you could say a probabilistic argument that there's a high probability that this jump happens and a high probability that that one happens, right? But even if these were high probabilities, at the end of the tail there, you still probably have a slippery slope argument. Why? Okay, right. Because even though each jump has a high probability, the probability of this jump happening and this and this and that and that and that, how many jumps are there? 1, 2, 3, 4, 5, 6 jumps. What's the probability that you make it all the way to the end? Right, you guys all do that? Good. What was it? 73.5%. And so you keep adding jumps, that number goes up, and then the argument gets weaker and weaker and weaker because the argument is based that you go all the way down to the bottom of the hill. All right, is everyone okay with that? So that slippery slope argument is how high a probability in each step, and then how many steps is it going to take you to get from the start to the finish. Okay, so that's what we're talking about here in the multiple testing problem. If you think about what we're doing is we're doing experiments, and we are very soon going to be setting up experiments to detect if something is real or not, or if this effect is real. And so what we're going to be looking at is the alpha value, the alpha error. Let's focus on that for a minute. So the alpha error is the null hypothesis is what? Is true, but I reject it. Right? So if I do a 5% level test, if I do one of them, 5% of the time I make an alpha error, right? What if I do 10 tests? What's the probability that I make at least one alpha error? How do we figure that out? Let's think about it. So I have 10 tests. Let's say alpha is 5%. What's the probability that I make at least one alpha error? So that means in those 10 tests, I reject the null hypothesis, even though I shouldn't. The multiplication rule? 40%. So you would say it's, well, let's say, what's the probability that I don't make an alpha error? Is it that? Yes? Who thinks it is? So if that's a probability that I don't make an alpha error, what's the probability that I do make an alpha error? 1 minus that. Okay. I'm not sure what that number is. I made all those numbers up. What is it? We always like to get a number at the end of it. 40.1. Okay. That's pretty high. It's higher than 5%, right? Okay. The other example that you could use is if you think of, if you're hanging out in your dorm room and you're bored and someone says, hey, here's a revolver, let's play Russian roulette, right? And you say, okay, I'll do it. That sounds great. I have a 1 in 6 chance of dying, right? But if you play it over and over and over and over again, your chances of dying go up, right? Every time you do a test, you risk getting an alpha error, and then if you look at the whole experiment, if you will, which is the collection of all the tests, we have to be worried about that. So we're going to try to balance that when we look at alpha error. There's alpha error of a single test, but when we're going to be doing a lot of tests, we have to at least be cognizant of the fact that the chances that I make one alpha error are more than 5%. It depends on the number of tests. We're not going to do a whole lot with this, but it's going to come back at the end of the class when we have a procedure for how to reduce our full model to a parsimonious model. We will revisit this multiple test problem. So how the book handles this is there's the Bonferroni method, which is pretty straightforward. It says you take these p-values that you have and you multiply them by the number of tests that you do, and that gives you that experiment-wise or corrects for the multiple testing problem. Okay. Right, so you'd say you've done 4 tests. If you multiply each of these p-values by 4, that gives you the corrected value of the p-value, and you'd say the only one that really stands out would this formulation C would stand out. The other ones, well, they didn't stand out before. They don't stand out now. So there are different ways. If we make it to the analysis of variance part of the course, we will look at other methods as well. So in statistics, we have to be aware of this multiple testing problem. Yeah. You multiply them by 4, and then if alpha is 5%, you multiply each by 4, and then you compare them to your hurdle value. So if this was 0.02% and you didn't have the multiple testing problem, you'd say, oh, that was significant. Formulation A is really doing something. It had a low p-value. We reject the null hypothesis. null hypothesis in this case was that it wouldn't be doing anything. But after we take that 0.02 and multiply it by 4, we would say, oh, that's greater than 5%, therefore we wouldn't say that formulation A is doing something. And this Bohm-Ferroni method is just a very general kind of first pass correction for the multiple testing problem. And we're not going to do a whole lot with it at all now, but we will revisit it later. So I just want to just get that concept of every time you do a test, you have, if it's a 5% level test, you have a 5% chance of making a alpha error on each test. Okay, so let's move on here. Now we'll maybe finish chapter 6 today. So make sure to print out the notes that are labeled DOE 1 and DOE 2 for next time, because DOE 1 is we're going to go real fast through that. Probably not even going to spend a day on it. So. F-test. Okay. We've been doing tests on the mean. We've been doing tests on the difference between two means. We've been doing paired difference tests, but they're always been on the difference between the mean values, if you will. We always have been working with a mean value in each one of those cases. The mean value of this data set, for example, and this value of this data set. But one of the things that is really important in engineering and quality control is not only, well, what's the average value of these data, but what's the noise of the data. So sometimes we can make, very often, we can make changes to our process, say a chemical or a manufacturing process that we're working with, and the goal isn't to increase some mean value, make a higher concentration of stuff, but the goal would be to reduce the variability of whatever we're making. So very often we are concerned about how do we take that variation, and I could write it in terms of standard deviation or variance, it doesn't matter, but we're looking at how do we decrease the noise in what we're doing. So as I mentioned before, that's one huge area of quality improvement is how do we reduce the noise. So a measure of quality is we make the same stuff and we make it almost exactly the same every time, which means we reduce the noise. So one thing that we would be interested in would be an hypothesis test. That test, did I reduce the noise or not? I went in there, I fiddled with the machine, I reset things, I recalibrated some stuff. Did the noise go down? I've got one data set, I got a sigma squared of 10. I got another data set, I got a sigma squared of 7. Okay, it seems lower. Is it significantly lower? Right? So we're always asking that question. Is it low enough that we could say, yes, it's significantly lower? Okay, so we are going to do a hypothesis test on the variances. And please be really careful. So on the last exam, we had to be careful about doing the right test. And the right test we had to decide was, is it a difference between two independent data sets where it was x bar minus y bar, or were they paired differences? On this upcoming exam, we'll still have that problem. And then we have this problem is, am I asking you to do a test on the means, or am I asking you to do a test on the variances? So it's very clear because it'll be written right in the problem. It'll ask you to, are the variances equal? But it's easy on an exam to read that over quickly and miss it. So please make sure you're very careful on the next exam also that if I'm asking you to compare variances, you don't compare means instead. Okay, so the distributions that we have, our statistics that we have, T and Z don't help us out. The distribution, or the distribution that we have that models variances, and we're just kind of present it without development, is the F distribution. So there's a chi-square distribution that describes variances, and the F distribution describes ratios of variances. So it would be sigma 1 squared over sigma 2 squared. We're going to go to a new distribution called the F distribution to get areas under the curve for this sort of situation. So that means because this is the statistic that we have, we're going to get our null hypothesis in that form. Just like when we had mu1 is greater than mu2, we moved it over. Just like before when we did this. We switched that to mu1 minus mu2 equals 0. So when we do this as our null hypothesis, we are going to get them in terms of a ratio. So not a whole lot of fancy math happening there. So what are the null hypotheses that we can come up with? That ratio is less than 1, that ratio equals 1, that ratio is greater than 1, and then the alternative hypothesis is just the other side of those. We can have one-sided and two-sided tests just like before. We go to our data, we calculate that ratio, that gives us an F. We can compare it to an F star, or we could go from F to a p-value and compare with alpha as before. So almost everything is as before, except we're working with a ratio of two variances. Okay. So there's one more twist, but I'll wait on that until we at least get this stuff down. Okay, let's look at this example right here. So I want to read through that. Just take a minute. Do that, please. Okay, do those hypothesis tests look right? Focus on the question we're trying to answer, tips us off to the alternative hypothesis. The only way we can prove that is by disproving the null hypothesis. And at least the first few times, let's write it like this, and then we can get it into a ratio. Right? So sigma squared A over sigma squared B greater than 1. Everyone okay with that so far? So then we assume the null hypothesis is true, which sets this F distribution. It doesn't center it because we're not dealing with means. And now would be a good time to look up the F distribution. Back of the book, bunch of tables. One of them is labeled the F distribution. So we're going to test this with our statistic. 2.3 over 0.6. So okay. So we go to our data. Our data seems to indicate that the variance of 1 is greater than the variance of 2. And we get an F of 3.833. Okay, so then from that, that's just like our t, we would like to get a p-value. But like t, we need to know something more. Anyone find that distribution? You got a page number? 814. So there's our table of the F distribution. (814). What do we have to know before we can find the area? Degrees of freedom. So remember, our degrees of freedom are how many degrees of freedom went into the noise. And for this test, we have two values of noise. We're not going to assume they're the same, right? Because we are testing if they are the same. So we need to know how many degrees of freedom went into that one, how many degrees of freedom went into that one. So we have 5 and 9. So we'd say F5, 9. And then we would say some alpha value. And then you have to look at your table. So you have degrees of freedom going across the rows at the top, columns on the bottom. Which one corresponds to the numerator? Can you tell based on the cartoon? The row across the top, is it this one or this one? Should the top one be 5? Top one's 5. As I recall on that table, the top row is the degrees of freedom in the numerator. Bottom is, or the first column is the degrees of freedom in the denominator. So you look at 5 and 9. You should be able to locate 3.48 as the value for 0.05. And so it lists 4 areas there, right? These right here? Okay. So it lists 4 areas. It doesn't give you a lot of information. It gives 4 areas. So you see for the area of 0.05, and you get 5 degrees of freedom and 9 degrees of freedom. Do everyone see where that 3.48 is the value on the table? So that's the F value that corresponds to that 0.05 row with 5 degrees of freedom in the numerator and 9 in the denominator. So be sure you can locate. So these numbers are in the body of the table. These are various rows associated with the top degrees of freedom and the column degrees of freedom. Yes?
So that 0.05 is basically helping us find like a total value.
Yeah, the 0.05 is the area. So it lists 4 areas. So 0.05, what, 0.1, 0.05, what else? 0.1, 0.05, 0.01, and 0.001. So we can do only those level tests in our situation. We're just limited by how much information they can put on the table. If you go do this in Excel, you can do any area you want in that way. Is everyone okay with how you find F from that table? The mechanics of it. Okay. The last thing is in that table, do you see an F less than 1? What's the smallest F you see? Okay, so I'll tell you the answer. because it's almost time to go. So that table only gives us the upper tail of the distribution. It doesn't give us this tail, which would be 1 over that f, just because it's hard enough to get all that information there. So we have the choice when we calculate this f, you know, which variance do you put on the top, which on the bottom, right? That's pretty arbitrary. So because our table only lists the large values of f, we put the big one on the top and the small on the bottom. So your f's are always going to be greater than 1 to get the value off the table. In Excel, it doesn't matter, but just that's when you're doing these problems, we're going to have to think about, oh, do we say this is greater than that? And we're going to get the ratio always greater than 1. Okay, see you tomorrow, Wednesday.